All right, we are recording. Give it something to focus on there. Okay, I just sent out a notice about a possible field trip to LIGO. Actually, I'm telling LIGO to go ahead and schedule it. So I'll be going with however many students can make it. It would be Friday, May 17th, which is a week from this Friday, only 9 days away. They must have had a cancellation, and so a spot opened up for us, and I'd like to grab it for you, those of you who can make it. It really is a world-class research facility, and there's one other one as good as it in Livingston, Louisiana, and they need two of them to make sure that they get a real gravitational wave signal. But I think you'd enjoy it very much. And if I think what we might do next week on our Tuesday meeting is maybe have a bit of an introduction to general relativity. And there's a video we could watch that is available from LIGO. And you could learn a bit about gravitational waves. So anyway, I sent out a thing. If you cannot make it, I'd like to know about it so I can, have some estimates of the number of people who will be able to do it. So please pay attention to that. All right, on to the topic for today. We've been looking at the effects that magnetic fields have on moving charges and electric currents, but we haven't been talking about how magnetic fields get produced in the first place. And so that's what we'll be doing here for the next few days. And actually, it's stating how they get produced. Moving charges make magnetic fields. So that's how they get produced. But looking at the details of different moving charge configurations, like a long straight wire or a coil of wire or a toroid or various things like that, we'll be examining them. And there's a magnetic kind of corollary to Gauss's law. Actually, if you use Gauss's law for magnetism, if you remember for electricity, you have that the flux of the electric field is an integral over a closed surface of E dot dA, and that equals the charge that's enclosed by the surface, the net charge that's enclosed by the net surface divided by epsilon naught. The mathematical version of Gauss's law, which is called Gauss's law for magnetism, would be it's got a phi sub b, so it's the flux of the magnetic field, and it would be the integral of B dot dA. But this one's kind of anticlimactic. It's equal to zero. So, and this is that statement that there's no such thing as a magnetic monopole, which is what a free charge would be, like an electron or a proton or something like that. Magnetic fields always occur with both a north and a south pole, which a north pole by itself or a south pole by itself would be like a free charge for magnetism, but they never happen. They're always in pairs at the simplest level. And so that one's not too interesting. However, the magnetic field of a moving point charge, we can do something about. And for a point charge, it would be, now this is going to be a little bit of a weird expression here, but mu naught over 4 pi. Mu naught is a fundamental constant of nature, and it shows up with magnetism, basically, but also electromagnetic waves. Anyway, we have this, and then we would have Q V cross R hat. That would be a unit vector since it's got a hat divided by R squared. Now, this is kind of weird, but let's go through it part by part. First of all, this constant, mu naught is equal to 4 pi times 10 to the minus 7th Tesla meters per amp. Okay, so that's pretty weird. You've got mu naught over 4 pi here, which basically means you could replace this constant with just 1 times 10 to the minus 7th Tesla meters per amp. But it's written in terms of the mu naught because in some geometries you're going to be doing things with the expression that'll make make the 4 pi go away possibly. And also mu naught is a fundamental constant of nature. It's one where I remember the expression right, the speed of light is like 1 over the square root of mu naught times epsilon naught. I'm not positive about that, but because we never get to that part in this class. But anyway, that's what this expression means. Now it's got a cross product in it, as has just about everything we've done with magnetism. But geometry wise, if you had a moving charge here and it had a velocity v in that direction, and then this v that's in that direction is a line, and so you can imagine extending it into space. If you add to that a point P where you're going to be calculating the magnetic field at, then this line and P determine a plane. So that gives you a plane to work with. And the r hat will be a unit vector that points from where the charge is at some instant. So this would be r hat. The distance at any given instant between the charge and the point P is what we would call the r. And you can see from this, it's an inverse square law force, so it gets weaker with the square of the distance, like the electric field for a point charge does, and like the gravitational force does. So we've got that. And then the V cross R hat, point your fingers in the direction of V so you can curl them in the direction of R, and your thumb will point into the page here. That means the magnetic field out here due to that point charge is going to go into the page. So when that's the case, we draw a little X at that point, and that would be the magnetic field just due to that little charge there. Not going to be much when you've got a times 10 to the minus 7th here, and a typical charge for something like an electron or a proton is 10 to the minus 19th coulombs. Even if you got a really big speed on the thing, it may not be large unless you're really close to it, like say an atomic radius away from it. Then you might have a reasonably sized magnetic field. So, but it's going to be, we're going to have to be thinking about these things carefully to calculate them. Okay, there it is for a single point charge. When you have an electric current, you've got a whole bunch of charges moving. So let's imagine that we have a wire here, and we'll just suppose that this is the chunk of wire we're interested in, and it's got a current that's flowing in that direction. And this would be a little chunk of the thing, and I'll say that it has a length dl, and we'll have a unit or a vector here that we'll call dl, and that'll be a vector that points in the direction of the current flow. So we'll have that. And the magnetic field at a point P out here that's produced by this little bit of charge, I'm going to draw the unit vector elsewhere on this one. But this will be the distance r again. And again, imagine this is basically an infinitely thin wire. So there's r. R hat is going to be a unit vector pointing out in that direction. And unit vectors actually, if you take this angle and define a coordinate system here that has x that way and y that way, the unit vector r hat could be written as the cosine of theta in the I hat direction plus the sine of theta in the j hat direction. And you know it'll be a unit vector because the magnitude of r hat will equal the square root of the cosine squared of theta plus the sine squared of theta. Okay, so that tells you it's got a magnitude of 1. I saw on the test that I just gave back yesterday that some people had a unit vector. Well, they had a vector that pointed in the direction of something, and they thought their unit vector would equal, I think it was 8.00 times 10 to the minus 6 meters in the I hat direction plus 16.00 times 10 to the minus 6 meters in the j hat direction. That's not a unit vector. If you calculate the length of this vector, well, for one thing, it's got units, and unit vectors just have direction. They don't have units. So you could cross those meters out, but even then, its length or the magnitude of this vector is going to be something like 17.9 times 10 to the minus 6 meters, if I remember right. But what you could do to make this a unit vector is to divide this by the length of the vector there, and that turns it, if you divide any vector by its length, you turn it into a unit vector. So here you'd have to have 8.00 times 10 to the minus 6 meters squared plus the 16, and that would give you a unit vector, but it's a whole lot easier to use the cosine and sine thing. And if you you've got 16.00 micrometers here and 8.00 micrometers here, just figure out theta. It's the arctangent of 2 in this case. That'll be theta, and then the unit vector is the cosine of that angle plus in the I hat plus sine of theta in the j hat. Anyway, that's a little bit far afield. I still haven't told you what the electric or the magnetic field due to this current element is. It will be this, dB, the magnetic field caused by this little tiny chunk of length in a wire carrying a current in that direction, will equal, it's got another mu naught over 4 pi in it, so that'll be common to a lot of our expressions, and it will be I dl cross r hat over r squared. So we're going to have to use this expression to calculate magnetic fields of currents, and we'll do a few examples with that today. But for a first problem, I'm going to excavate my calculator so I can find it when I need it. It says calculate the magnetic field at a distance of 5.3 times 10 to the minus 11th meters for an electron moving at 2.2 times 10 to the 6th meters per second. Now that distance happens to be the Bohr radius, so we'd be calculating the magnetic field that a proton experiences because of an orbiting electron, if that's the way atoms behaved. But anyway, assume the electron is at its closest approach to the field point, so the cross product will have a 90-degree angle in it. Okay, well, let's see how this will work. We'll just imagine here that the path of the electron is along this line, and at some instant, it's right here. So here's our E minus, and this will represent the velocity. Okay, and then it's at its closest approach. So it's been traveling along this line, and right now, here's the point P where we're going to be calculating this. And the distance here, 5.3 times 10 to the minus 11th meters, is going to be the separation between the electron and the field point here at this instant. So this is R in our expression here. And because this is just a point charge, we're going to be having the magnetic field of this is going to equal that expression for the moving charge, mu naught over 4 pi times QV cross R hat over R squared. Well, I've got enough information here. I could actually just set up a coordinate system and let this be I hat. I could write R hat in this case is just going to equal I hat. V is going to equal the magnitude of it, but in the J hat direction. So I'm just imagining a coordinate system here with X pointing that way, Y pointing that way, X, Y, and Z would be a vector that points up out of the page. So Z is going to be pointing at you out of the page here. All right, do we have enough information? V cross R hat. Well, this would be our R hat direction. It's just like the I hat. In fact, it's the same vector because they're equal to each other. V cross R hat, point the fingers of your right hand in the direction V is going, cross them in the direction of R, and your thumb will point into the page. And that's a right hand rule. You have to use your right hand. But V cross R hat is going to be into the page. It'll be in the minus Z direction, but the charge on an electron is negative. That'll reverse the direction of the cross product and make V cross R hat point in the Z direction. So plugging all this stuff in, we'll end up with B is going to be mu naught over 4 pi, and I'm going to leave that alone for a minute, over 4 pi. And then for the charge, I'll have minus 1.60 times 10 to the minus 19th coulombs. V, I'm running out of space, typical. Let's see, I think you can still see all the stuff I've written on here. 2.2 times 10 to the 6 meters per second is the magnitude of V. Let's see, and then I need to account for that V cross R hat. Okay, well, I've got the V, the magnitude of V here, and V is in the J hat direction. So what's left that I have here is actually going to be J hat crossed with I hat. And we may have talked about this. And then down on the bottom, I'll have the 5.3 times 10 to the minus 11th meters squared. So we'll see how the units work out here in a minute. But J hat cross I hat is the minus Z direction, but when we multiply it by that minus sign, we'll get something in the positive direction. But this little product here is equal to minus K hat. So that'll be that. So now we can plug in all our numbers. We know this minus and that minus will make this thing be in the K hat direction. And by the way, when we start doing calculations for magnetic fields of currents, you can always, one of the things we'll do is a long straight current at first. And you can always, that long straight current is a line, your field point is a point, and the point and that line will determine a plane. So your magnetic field will either point into the plane or out of the plane. And so we'll have that simplification. But stuff we'll have to keep doing is using the right-hand rule for these calculations. So anyway, in this case, I will have, now I'll take into account that mu naught is 4 pi times 10 to the minus 7th, and mu naught over 4 pi is going to be 1.0, and I'm only keeping two sig figs. It's 1.0000 times 10 to the minus 7th, and that's Tesla meters per amp that I have for units on that thing. And then I'm going to take this minus sign out of here and attach it to that minus K and make it a plus K. So I'll have the 1.60 times 10 to the minus 19th coulombs. And then I'm multiplying by, let's see, 2.2, whoops, 10 to the 6th meters per second. And I'll have a K hat at the tail end over here, and then I'll divide by 5.3 times 10 to the minus 11th meters squared. All right, so how are our units going to work out here? Well, I have a Tesla over an amp. Here I've got a coulomb times a meter per second. If I take that per second and put it under here, that gives me an amp, coulomb per second, and that'll divide out with that amp. So I'm going to cross this out, and this out. And then I will have a meter left on top and a meter squared on the bottom. That leaves me with a meter on the bottom, and there's a meter there. Or I could think meter times meter is meter squared. I'll have meter squared on the bottom. The meters are all gone, and I'll get a magnetic field strength in Tesla. So yay, that'll be right. And now it's time to just plug in the number here. Not much of a magnetic field, I'm guessing. Clear that. Actually, that's 10 to the minus 22. I bet I made a mistake on here. Like forgot the charge of the electron. Yes, I did. Yep. I forgot the electron charge. Okay, I'll just take the result I got and multiply it by that. Then you can check this yourself to see if I screwed up the thing. Actually, I get a reasonably strong magnetic field. Well, to two significant figures, I get 13 Tesla. I want to make sure I didn't make a mistake on that. 10 to the minus, that's 10 to the minus 26. That's 10 to the minus 20. 10 to the minus 22. Yeah, that's probably about right. So 13 Tesla in the K hat direction. So that's interesting. The proton, when that electron's whirring around there, would actually experience a pretty strong magnetic field. And the electron would also, from its perspective, it's the proton that's circling it, and it would be experiencing a field that's just as strong. So kind of interesting. There are magnetic effects that show up in these things. Okay, so that's a sample problem for a single point charge moving along. That a pretty good clip. So we can move on from that and try a current. And this is to calculate the magnetic field at a point P, a distance x, from a straight wire carrying a current I. Necessary dimensions are shown in the drawing. So let's see. Yeah, we just have letters for these things. So minus y1 to y2, x is going to look like that. And I think I'll pick a little chunk of current here. I'll have my DL be down here. So DL will point up in that direction. If they're calling this X, I think I'll let the X-axis point in that direction and Y point in this direction. So DL all along this wire is just going to equal dy in the j hat direction. Okay, remember the DL vector points in the direction of current flow, which in this case is in the positive j hat direction. So I have that. Now it's going to be a little bit tricky here, figuring this one out, because we're going to have to consider some components of vectors. Here's going to be our r hat vector here. And if this is the angle theta here, this would also be the angle theta here. And I guess my r hat, I could think of it as being cos theta in the I hat direction plus sine theta in the j hat direction. So I have that. Let's see. And what about theta? Oh, and this distance here is going to be r. The magnitude of, oops, this is r hat, excuse me. The magnitude of the distance between those two things, this would actually be y down here. But r will equal the square root of x squared plus y squared. The cosine of theta is going to equal x over the square root of r squared plus x squared. And the sine of theta will equal y over the square root of, that's supposed to be y squared plus x squared. But let's see, something else I need to do. I want theta to be a positive angle when y is actually negative. So if I put minus y, that way when I'm in the negative part down here, I'll get a positive value for theta. And once I get above there, I'll have a negative value of theta, which will turn the y component negative. So I think I've kind of set this up the way I need to now. For my dB, it will equal mu naught over 4 pi IDL, but my DL is dy in the j hat direction. Let's see, crossed with my r hat, which is going to be cos theta in the I hat direction plus sine theta in the j hat direction. Oh, this is a multiplication sign. I don't mean to write x in here. Oh, no, it's a cross product. That's what I want. Crossed with. And the j hat crossed with j hat is 0, a vector crossed with itself. So really all I'm going to have is j hat cross I hat here. And that's going to be in the minus k hat direction. But then on the bottom here, I also have r squared. which is actually x squared plus y squared. Okay. That means this is going to simplify to, let's see, dB is going to equal u naught over 4 pi. Now, j hat cross I hat, j hat cross I hat's going to point in the minus k hat direction. So that'll be that, but I will have I dy cosine of theta, and then the j hat cross I hat will be the minus k hat direction. So I'm going to save that. The j hat cross j hat part vanishes, so I don't have that. I'll only have this. And I've got I dy cos theta divided by x squared plus y squared. Now I can reintroduce my expression for the cosine of theta here. And it will be, I'll have mu naught over 4 pi. I'm going to take the dy and put it out here at the end. And then the minus k hat as well. And the cosine of theta has x over the square root of x squared plus y squared. I've already got an x squared plus y squared down here. That will end up giving me x over x squared plus y squared. And this will be to the, this is like the 2 halves, and then I've got another 1 half. So this will be to the 3 halves here, is what I get there. Okay, now remember, x is a constant. It's just that thing. Our variable here is y. And so to get the full magnetic field, I'm going to pull all the junk out of this expression that's constant. And in fact, it's the entire numerator and the 4 pi there. So I'll have b will equal the integral for y going from minus y1 up to y2. And then, whoops, well, I'll just wrap them in parentheses for now. Mu naught ix and minus k hat. All of those things are constant in this expression. And the 4 pi down there. And then the part that actually matters, I've got a dy. Well, all of it matters, but this is the part that I have to worry about for my integration. And there I have it. Okay, so this shouldn't be too bad an integral. Then we'll save that minus k hat at the tail end. We'll probably write this down. Over 4 pi. And then I'm just integrating this dy over x squared plus y squared to the 3 halves. Now, that happens to be one of the integrals that is on the formula sheet that I gave you, because they show up in this unit a few times, and I don't have that memorized, but I do have it. It is in the back of your book in the appendix, and I think it's the very first appendix. Appendix E. Okay, it is for my book, it's appendix A4. It's one of the integrals. Let's see, it's got dx over x dx over that to the 3 halves. Here it is. It has dx over a squared plus x squared to the 3 halves. For us, it's going to be the other thing. But anyway, this integral ends up being, it'll be 1 over x squared. I'm having to translate this from having x as the variable of the integration to y. And we would have y over the square root of x squared plus y squared. Let me make sure I've copied that correctly. Whoops, it's supposed to be x squared here is what we've got. And then we would be evaluating that at minus y1 and at y2. I think. Now, let me make sure I translated that correctly. I'll show you what the integral looks like here. It's this little one right here. And if you can read that there, pretty sure I've got it right. Now remember, our variable of integration is y, so we had dy, and we could think of this as y squared plus x squared, and the a squared comes out over here, and then we'd have y over, I hope I wrote y, yes I did. Okay, so what's this going to look like? I've got an x here and an x squared there, so I'll have mu naught I over 4 pi x, and that's in the minus k hat direction so far, so it's going to be into the page. So this entire stretch of wire here will work together and make an a magnetic field that's into the page. So here's something you can imagine. This is another right-hand rule of sorts. If you point the thumb of your right hand in the direction of the current flow, your fingers will curl in the direction of the magnetic field. And actually, the magnetic field of a straight wire is a circular pattern. If you look down the wire, so you're looking down the wire with the current going into the page here, the magnetic field at any point forms circles around it. So that's what it looks like, although those don't look much like circles. All right, but now we have to evaluate this thing. I pulled the 1 over x squared out, and what I'll get out of this is y2 divided by the square root of x squared plus y2 squared minus, actually, it's minus a negative, so it's actually, well, I'll go ahead and write it up here, minus y1 over the square root of x squared plus y1 squared, and in here the y1 is squared, so you don't have to worry about its sign, but this ends up minus and a minus is a plus. And here's the thing, y1 is this distance down here, okay, minus y1 is what showed up in the integral, but y1 is this distance. This is the square root of x squared plus y1 squared. Well, this is the opposite side of that angle, and this is the hypotenuse. Up here we've got y2, but what this ends up being is this. It turns into mu naught I over 4 pi x in the minus k hat direction, but I'm going to stick that out at the end. But it ends up being the sine of theta 1 plus the sine of theta 2. And I swapped the order of addition here, but it's commutative, and it's in the minus k hat direction. Those are just the angles here and up here. This would be theta 2 up here. Theta 1 would be the angle all the way down here at the bottom. Now, what happens if you get a really long angle or a really long wire? theta 1 and theta 2 go toward 90 degrees, and you'd end up with 1 plus 1 here. That's 2. And so you'd end up having something like that. So for a really long wire, grab a blank sheet of paper here, with a blank on one side. For a very long wire, the magnetic field strength is going to equal, I just take this thing and stick a 2 on top, which will divide with that, and I'll end up with, it'll be mu naught I over 2 pi x, where that's how far away from the wire you happen to be. Well, that's not a bad expression. That means looking down this wire in this direction, you get these circular magnetic field patterns around that, which is sort of what Faraday was imagining in that film that we saw the other day. But if this is a distance x out here, this would be how strong the magnetic field happens to be there. So it drops off with 1 over the distance from the wire, and not like 1 over x squared, because we're imagining an infinitely or a very long wire, or close to a wire that's not infinite, but something else. Okay, let's try another problem. That one took a while, but we really got a useful expression out of this. And they do this, something like that in the book, I think, for an example. So we have a long straight wire running in a north-south direction, is 0.65 meters above a compass. How much current must flow in the wire, and in what direction to make the compass needle point 30 degrees east of north? Huh. Imagine it's at a location on Earth where the compass would ordinarily point due north, and you may use B sub E equals 0.55 times 10 to the minus 4th Tesla for the strength of the Earth's magnetic field. This one's a little bit hard to understand, but here's the idea. We'll imagine that here is our wire, and we're looking down the axis of the wire here. The compass needle is 0.65 meters, or the compass is 0.65 meters directly below this wire. Okay. Now, if the current was going into the page here, to draw some headings here, we'd have west in this direction. We're looking north in the picture that I've sketched here, and east in this direction. So a current that was going into the page would produce a magnetic field that points west. We're going to need a current that's coming out of the page. So we're going to have to be, we're looking north here. And so I need to draw a dot here as if the magnetic field is coming, or the current is coming out of the page, and that will produce a magnetic field here. And this is, I'm going to call it B sub current, where that's the magnetic field of the current. Then, if we look from above down at the magnetic field currents that we've got at this point, from above, change our viewpoint. Said, let's see, the compass would ordinarily point due north. So this would be B sub E is pointing in that direction. And we're kind of looking down at this point here, and we've got a magnetic field here, B current, pointing to the east, and the result, this would be B current again. This is the resultant magnetic field. B, call it B sum, but it makes a 30-degree angle with due north. So, well, we can actually figure that out. The B current over B sub B is going to have to equal the tangent of 30. So this is magnitude-wise. Because when they add together, they produce a magnetic field that points 30 degrees east of there. Okay, let's see. That means B current is going to equal B sub E tangent of 30. And I'm just going to take B sub E there and multiply it by the tangent of 30. So on 0.55 E minus 4, they probably wrote it this way because 10 to the minus 4th Tesla is a unit of magnetism, magnetic field strength called a Gauss. And that's often the way that the Earth's magnetic field is expressed, is in Gauss, because it's around 1 Gauss at most, or a small fraction of it. But anyway, that thing times the tangent of 30. And is this one, it's in degrees, good. So I'd get about 0.32 times 10 to the minus 4th Tesla, or 0.32 Gauss for the magnetic field of the current that we have here. But we've got an expression for the magnetic field of a current when you're a distance away from it, that magnetic field will equal mu naught I over 2 times pi times x. And we just figured out what the magnetic field is, the current. It's got 2 R's, but I'm just writing it as a mess down here. So it'll equal that. We know that x, in this case, is just the distance away from the wire. It's the 0.65 meters, and I need to solve for the current. I already figured out that the current has to be pointing in the south direction, because if we're looking north, it's an arrow coming, or a point coming at us. So current points south. I just need to know what I is. So I is going to equal 2 times pi times x times B current divided by mu naught. Okay, now I can plug in all the numbers and see what I get here. 0.32 times 10 to the minus 4th Tesla. On the bottom, I will have, oh, that's x. It's not times. It's my 0.65 meters. Okay, and then on the bottom, I've got mu naught, which is 4 pi times 10 to the minus 7th Tesla per amp meter. Let's see. Teslas go away. Oh, no, it's Tesla meters per amp, I think. Yes, Tesla meters per amp. Okay, that makes the meters go away, and I'll end up with amps, which is what I hope for a current. Okay, 2 pi over 4 pi is just a 2 left on the bottom, so I'll have 2 times 10 to the minus 7th. So shortening this calculation, 0.65 times 32 E minus 4. Divided by. And this is a big current. And I guess it makes sense. I've got a minus 4 up there and yeah, I end up with about 1.0 times 10 to the fourth amps, which a power line might have that much current in it. I don't know, but that's a lot of current if you're going to deflect a compass needle by that much when you're 0.65 meters away from it. So kind of impressive. Anyway, at least if I plugged everything in there right. But pretty sure that's how that one turns out. We've got time for one more here. This is a very similar problem. We've got two hikers reading a compass under an overhead transmission line that's 5.5 meters above, so it's a lot farther away from them. Carries a current of 800 amps in a horizontal direction from north to south. So from north to south, if we look down on this thing from above, if this is north and this is south, we would have 800 amps going on here. And find the magnitude and direction of the magnetic field at a point on the ground directly under the conductor. So now we can imagine we're looking north, and it says it's going from north to south. So this would be a looking north viewpoint. So we just imagine dropping ourselves down to the level of the wire and looking up the wire, and the current would be coming out of there at you. So there's the current. And we want to know the magnitude and direction of the magnetic field at a point on the ground directly under the conductor. So we'll come down here. We want to know the magnetic field here, and this is 5.50 meters below it. And this result that we figured out for the very long wire, actually, I'm going to write it in a somewhat different way now. I'm going to call it mu naught I over 2 pi r, where r is the distance away from the wire, and that'll be that thing. So one hiker suggests they walk another 50 meters to avoid inaccurate compass readings caused by the current. Well, let's see if it's going to be a problem. Okay, the magnetic field down here will be 4 pi times 10 to the minus 7th, Tesla meters per amp. And then I multiply that by the current, which is 800 amps. And down here, I'll have 2 times pi times 5.50 meters. Okay, well, the pi's divide out. 4 over 2 is going to leave me with a 2 up here. So took care of all those stuff. And so 2 times 10 to the minus 7th times 800 divided by 5.5. So let's see how it comes out. And I get 2.91 times 10 to the minus 5th Tesla. Oh, by the way, the meters divide out, the amps divide out, so I do end up with Tesla. Well, that's actually 0.29 times 10 to the minus 4th Tesla. So yeah, the current could be a problem. That might make your compass point. Well, let's see. Magnetic field of this wire, if it's coming out that way, is going to point east again. I think we had a stronger magnetic field on that previous problem. Check it out. Where did I put that thing? I don't know. Lost track of it. Yeah, but anyway, you have the Earth's magnetic field pointing north, say at 0.55 times 10 to the minus fourth. And then this one is pointing east. I'm starting to wonder about that calculation I did on the previous problem, where I got such a humongous current. This is 0.29 times 10 to the minus fifth Tesla. So 0.29 over 0.55 is what I want. Yeah, it'd point off by about 28 degrees. So that's enough to get lost. So under certain circumstances, I've been out in the woods a few times where I had to use a compass to find my way around, and it's amazing that under certain circumstances, well, like one time I was in clouds, actually in the cloud level, and it was, you could walk 50 yards and you'd be completely off on your direction. So yeah, I'm wondering if I forgot something on here, because this is looking a little funky. I got an awfully high current on this thing. Although I don't see that necessarily did anything wrong. But that's an introduction to magnetic fields of currents. And we'll do a bit more with this tomorrow. I've got a few more example problems of this type, and get accustomed to doing these kinds of calculations. And so try to get used to those. Actually, for the last two problems, I was using the result of that previous one, where we found out that when you have a current in a long straight wire, you get a circular magnetic field, and it has that strength. So it's something we can use, but we can stop there. I think I haven't seen any questions pop up today, so I hope we're good to go. And see you tomorrow, and let me know if you would not be able to go on a field trip on Friday, May 17th. So read the announcement that I put out there.